All right, good morning, everybody. So for today, we'll start talking about Taylor series expansion. I remember last time we considered one example or one problem that was sent by one of our classmates, but I was quite in a hurry in solving that. So today, let's revisit Taylor series expansion and do a quick recap, and then let's try to answer some problems. So oh, by the way, if you still have questions as usual, just send them in the chat and I'll try to insert them during our discussions, all right? Now, so far, in the previous worksheet, what we did is to find a series expansion for certain class of functions that are related to a geometric series expansion, right? If you remember, we used the formula a over 1 minus r and say that it is equal to sum of ar to the n going from 0 to infinity. And we use this fact in order to get the series expansion for certain functions. For instance, 1 over 1 minus x, its derivatives and integrals, right? Though it's quite limited because the method that we use there is to find a relation between 1 over 1 minus x and the given function f of x. But for more general functions, we cannot find a relationship between these two. So we cannot simply integrate or differentiate or perform some elementary operations on some geometric series representing this guy in order to get the function f, right? So today we'll develop the more general approach on how to get a series expansion for certain functions, and this expansion is called the Taylor series expansion. So the Taylor series expansion around a number x equals a is given by this. Okay, your function f can be expanded in the form of a sum of f upper n evaluated at a all over n factorial times x minus a to the n, and going from 0 to positive infinity. This is a nice result because this will allow us to write any function as long as it has continuous derivatives of all orders as a Taylor series expansion. So let's break this formula down. So you have the usual series summation here. That's fine. And then if you know the center of expansion, then you know that your powers will be powers of x minus a to the power n. So this is a mainstay in the formula, all right? And then it goes with a bunch of constants over here. Let's start with the denominator. The denominator is fine. It's just n factorial corresponding to your index of summation. Now, the tricky part here is finding the numerator here. F upper n denotes the nth derivative of the function f. So if you want to have a clear and a nice formula for your expansion, we should be able to get a general form for the nth derivative of the function f evaluated at the number a. So remember that Taylor series expansions will only have the variable x in here because it's a common mistake among students that they forget that in the derivative, they need to plug in the center of expansion. So it is the nth derivative evaluated at the number a. All right. So we'll see some examples of these and how to find a formula for the nth derivative and try to see the pattern. But usually we don't deal with Taylor series expansion for for the common functions. We use the Mclaren series expansion. The Mclaren series expansion is just the Taylor series around x equals 0. So your f of x can be written as exactly this sum, the Taylor sum, or the Taylor series, except that your center of expansion is not the general number a, but is actually 0. So this guy simplifies to x to the power n. Because for most functions, it is easier to find a formula for the nth derivative when you plug in 0. All right. Now, I trust in the lecture that you already saw some basic series expansions. So maybe I'll just list them down here so that if you are reviewing using these worksheets, you have them beside you. So common series expansions. And I guess at least for the exam, you need to remember these because it will save you time if you know these expansions. E to the power x is the sum of 1 over k factorial x to the power k, k going from 0 to infinity. And here, since the subtrahend to x is 0, so you don't see an x minus a because a is equal to 0, you say that this is the Mclaren series expansion for e to the power x, or it's the Taylor series expansion of e to the x around x equals 0, right? What else? Maybe I'll just list this down also, but we already derive the formula for the expansion of ln of 1 plus x using differentiation of integration of a geometric series. But let's put it here. It's -1 to the power k of x to the power k plus 1 all over k plus 1, k going from 0 until positive infinity. Then we also have cosine x expansion, k from 0 to positive infinity of -1 to the power k, x to the 2k, all over 2k factorial. One way to remember this is that if you recall from trigonometry that cosine is an even function. So cosine is an even function. That's why in the expansion, you only see even numbers, right? Similarly, the sine function, we know from trigonometry, is an odd function. So its series expansion involves only the odd powers. So x to the power 2k plus 1 all over 2k plus 1 all inside the factorial, right? And I guess these are the basic series expansions that you have seen, all right? And let's see some more examples of several things that we can do with series expansions. But again, it's very helpful if you will remember these 4 formulas, all right? Let me see. John sent a question here. Okay, I can answer this question after I go to some more basic examples, John. So hold on. Yeah, let's put a pin on your problem. Okay, this is P4, 6 ln of cosine x. All right, that's fine. I'll go to that. But I would like to start with a simpler example. Okay. So here we want to find a series expansion about the given value of a for the following functions. Let's start off with x to the power 4 e to the minus 3x squared, right? So this is my function. Let's call it f. Say about or around x equals 0. What do we notice about this function? Well, this function involves x to the power 4, which can be treated as a series expansion of itself because it's just a power of x, right? So we can leave it as e's. And then we have e to the minus 3x squared, but we already know an expansion for e to the minus for e to the x, right? So so we can avoid going through this definition of the Mclaren series expansion because again my center of expansion is x equals 0. So I was supposed to use this, but this will involve differentiating the function f. And if you see here, my function f is a product. So if I will go through that route, I would have to take the derivatives or all the derivatives of f, look for a formula, plug it 0, and see if there's a pattern. That could be tedious because if you go to higher order derivatives, this is a product, so you will need to use the product rule. So the derivatives will become messier and messier as the order increases. So probably finding a pattern for this one is not worth it. But again, I note that x to the power 4 is just a simple power of x minus 0, so that's fine. And we already know an expansion for e to the x, so I'll take advantage of that. So let's see. So here we can recall that e to the power x has expansion x to the power k over k factorial, k going from 0 to positive infinity. All right. Now, this means that I can use the same formula, except that I will change all x's into negative 3x squared, because I'm after for an expansion for e to the minus 3x squared. And this is very similar to the left-hand side. It's just that the x was replaced by minus 3x squared. So that's what I'm going to do in this formula. I will simply replace all x's by minus 3x squared. So there's an x here, change it to minus 3x squared to the power k all over k factorial. And there you go. You have a nice series expansion for e to the minus 3x or e to the minus 3x squared without going through the tedious definition of the Taylor series expansion. All right, now let's try to simplify this a little bit. I'll play with loss of exponents so that we'll have a more elegant representation for the solution. K factorial is in the denominator. That's simple enough. Now here I have -1 times 3 times x squared all raised to the power k. So each of those factors will get a power k, right? So I can break that product up into the following. I'll have -1 to the power k, 3 to the power k, and then I was supposed to have x squared to the power k. But remember, loss of exponents say that if you're raising a power to an exponent, you simply multiply the exponent. So I can write it as x to the power 2k. Okay. Now, this is my expansion for e to the minus 3x squared, but we're looking for an expansion for x to the power 4 e to the minus 3x squared. So I can just have x to the 4th, and I'll replace e to the minus 3x squared by its series expansion. There we go. And I will bank on the distributivity of multiplication over addition. So this can go inside the summation, right? The basic distributive property they also hold for absolutely convergent series. So that's fine. So this will become the summation of -1 to the power k, 3 to the power k, and then x to the 4th times x to the 2k, multiplying powers of the same base. We simply add their exponents. So I'm going to have x to the 2k plus 4 all over k factorial. K goes from 0 until positive infinity. And that's my series expansion for the given function f, right? So this illustrates how useful it is to know the basic Taylor series expansion for the common functions, because that will save you a lot of work. Because again, if you did not use that formula, then you would have to take the derivative of the function f of all orders, or at least for the first few orders, and try to get the pattern when you plug in x equals 0. But that would be difficult, all right? So this is my recommended solution for this one. So at least for the exam, try to memorize the series expansions for the basic functions, all right? Okay, any questions so far?
Could you write out the summation for ln of 1 plus x really quick?
Oh, sure, yeah. I'm gonna flash it. I wrote it already here, so there you go.
Yeah, that one looks different from the one that's in the notes. In the notes, they have like, summation of k equals 1.
Yeah, I see.
Yeah.
So probably in the notes they have something like this, but those two are equivalent. I'm not sure what you use because different people have different preferences. Some will write it this way: -1 to the power k plus 1, x to the power k all over k. Is this the one in the lecture or
Yeah,
in your
that's one
notes?
lecture.
Yeah. Well, yeah, I chose this one simply because I want everything to start at 0, just to keep it uniform. But again, you can adjust the indices. So here, if I started at 0 and you want to start at 1, that means you are increasing the starting index. So the effect is that you need to subtract 1 from all the k's you see inside the sum, right? So when you decrease the starting index, you should increase everything inside. If you are increasing the index, you should decrease everything inside. So from here until here, what we did is to increase the index. So that in turn will require us to subtract 1 from all the k's I see here. That's why you get x to the power k instead of x to the power k plus 1. The k here was because we decreased k plus 1 by 1. A little bit trickier on the negative 1 to the power k. I could have written k minus 1. That's equivalent. But x plus 1 is also equivalent because this will just oscillate between plus or minus 1. Yeah. So the starting factor here would be k equals 0. So this would be 1. So we start with a positive term. So we want this summation to also start with a positive term. And let's check if k is equal to 1. I have negative 1 to the second power, which is also positive 1. So either k plus 1 or k minus 1 will work here. All right. So it doesn't matter which one you use. I just wanted to start everything at 0.
Awesome.
All right. So let's see. Okay. Any other questions before we proceed to the next one? I see that you guys are fewer than usual. Did the lecture again went overtime today? Or most of your classmates just didn't show up today? I see. Maybe because it's nearing the end of the semester, so they really want to finish everything up. But let's see. All right. Well, let's go to problem 2. Hold on, John, for your question. I'm going to start with a simpler example first. Or perhaps your problem is much simpler. Okay, yeah, maybe I'll start with John's question. Right. Let's try this one. Here, oh, but my instruction here is different. So how should I do this? So let me just put a star here. Find the Taylor polynomial. Because my general instruction is to find the series expansion, but I want to answer this first because this is much simpler. P sub 4 of x centered at x equals 0 for f of x equals 6 ln of cosine x. Because this will not require us to get a general formula or a general pattern for the nth derivative evaluated at f, because the nice thing about this is we are just looking for a truncated series. So I mean a polynomial with a finite number of terms, right? So here P4 means we are looking for the degree 4 polynomial. So the Taylor series is an exact match to f of x. So f of x is exactly the sum of the kth derivative evaluated at the center of expansion. In this case, it's 0 again, over k factorial x to the power k, as k goes from 0 to infinity. So to get an exact value for the function, we should take the summation until infinity. So, but in this problem, we are only asked to find the Taylor polynomial. And the Taylor polynomial is an approximation to the function f. So it is simply an approximation of a polynomial or via a polynomial of degree 4 for the function x. Because here, instead of using the entire summation, we will truncate the summation to the first 5 terms to get a polynomial of degree 4. So we'll have 5 terms, a constant, degree 1, degree 2, degree 3, and degree 4. So that's why we will get 5 terms here, right? So the degree here will indicate where you will stop, because this guy will be the exponent for your power. And again, this is just an approximation to the function f, because in order to get the exact value of f, we need to take the summation until infinity, right? Perhaps if we have time later, we can talk about errors involving this approximation. But let's do this one first. Find the the Taylor polynomial of degree 4. So we don't have a problem with this. They will just be x to the 0, x to the 1, x to the 2 until x to the 4th. The denominators would be from 0 factorial until 4 factorial. So the real challenge here is f to the power k evaluated at 0. So let's start doing that. When k is 0, we'll have f to the power 0, f upper 0 of x. But this is just your function f. And in this problem, it is 6 ln of cosine of x. And here we need to find f upper 0 of 0. So you plug in 0. Cosine of 0 is 1, right? Ln of 1 is 0. 6 times 0 is 0. Okay. Now let's do k equals 1. K equals 1, that will give us f upper 1. But f upper 1 is just another way of saying f prime. So we need to take the derivative of f. But for this guy, we need to use the chain rule, right? So this would be 6 over cosine x times derivative of cosine x, which is negative sine x. So when we plug in 0, what will happen? F upper 1 at 0, this will become what? Oh, that's a nice thing, because when you plug in 0, sine of 0 will become 0. This would be 6 over 1 times 0. We'll get a 0 again. Is that correct? Yeah, just double check my evaluations here. Then let's do k equals 2. That's f upper 2 of x. That's the second derivative. So we need to differentiate this guy. But this guy actually is just negative 6 tangent x, right? So if I differentiate negative 6 tangent x, let me put something here. That would be minus 6 secant squared x. All right. And then don't forget to plug in the center of expansion into your derivatives. We'll have f upper 2 evaluated at 0. What is secant of 0? Secant of 0 is 1 over cosine 0, so that's 1 over 1. So this guy would be 1 times negative 6, so this guy will be negative 6. All right. We cannot stop here because we're going until k equals 4. So let's try it more. K equals 3. We need f upper 3 of x. That's the third derivative of x. So we'll have negative 12 secant x times secant squared x, secant x tangent x, which simplifies to negative 12 secant squared x tangent x, right? And then if we plug in 0, what do we get? We'll get 0 again, right? Because secant squared is 1, tangent of 0 is 0, so everything goes to 0 here. Now the fourth derivative is a bit of a challenge, because here we need to use the product rule, right? So I'll have negative 12 secant squared x times the derivative of tangent x, which is secant squared x, plus I'll copy the second factor, tangent x, times the derivative of the first factor. So that's minus 24 secant x times derivative of secant, right? Negative 24 secant x, then derivative of secant. So we'll have secant x tangent x again. All right. But we don't need this very complicated expression. Remember, we need to plug in the center of expansion, right? To get f upper 4. F upper 4, plug in 0. This would be 1. This would be 1. So we'll have negative 12. And then if we plug in 0, there's a tangent here. So I know that's gonna be 0. So the entire second factor or second term will become 0. So f upper 4 of 0 is just negative 12. And now we can build up our Taylor polynomial P4. Remember, this is the sum from 0 until 4 of f upper k evaluated at 0 all over k factorial x to the power k. So when k is 0, we need f upper 0 evaluated at 0. We already knew that is 0. So I don't care about the other factors. I see a 0 multiplier. That's the end of it. Plus, what happens when k equals 1? When k equals 1, this factor luckily is also 0. End of story. I don't care about the other factors. Plus, when k is 2, we get negative 6. All right. So this would be negative 6 over 2 factorial times x squared. And then plus, if x is 3, the derivative happens to be 0. So this guy is 0. I don't care about this guys anymore. That's going to be 0. Plus, at k equals 4, we get negative 12. This guy. Over, we are at k equals 4, so there would be a 4 factorial in the denominator times x to the power 4. And then we'll just need to simplify. So this would be what? Negative 6 over 2x squared. I just expanded 2 factorial. And then minus 12 over, what is 4 factorial? 4 factorial is 4 times 3 times 2 times 1 over x to the 4th. I see 12s in here. So that means upon simplification, this is just minus 3x squared minus x to the 4th over 2. I hope I did the calculations right. Let me see. Minus 3x squared minus 1/2 x to the 4th. So I guess option E is the right one here, right? Provided I did all the arithmetic correctly. So hopefully I did. So any questions? All good? Okay, so you see here how tedious the process can be because we need to find all the derivatives up to high order. So for very complicated functions, looking for the derivatives would be hard, right? But for some simpler functions, we can get some patterns. And I guess that's how you already saw that when you derive in the lecture the expansions for e to the power x, cosine x, sine x, and what? I think, ln x, I guess also you did it in the lecture, right? Oh, no worries, guys. I heard that the lecture went overtime today, so no problems. So if you missed part of the lab discussion today, so you can just revisit the recording. So I'm gonna, it will be up in Teams shortly after we end the meeting, and it will be up in my website later in the afternoon. Okay, so let's try a more general one. If you don't have any questions for that, right? So for problem 3, I'm gonna go back to the original instruction. Number 2 was a exception to our instruction here. Recall for those who came in late, we're trying to find series expansion for the given about the given value of a for the following functions. So we just did example 1, and then example 2 was a question sent by John, which I think is from the practice test. Then let's write problem 3, and here we want a series expansion for 1 over x squared around x equals -1. All right. All right. So recall the general formula. Now we have a different center of expansion. Our center of expansion now is -1. So our function or our series will look like this. F upper k evaluated at -1. Remember, we're evaluating the derivatives at the center of expansion over k factorial times x plus 1 to the k. Or if you want to see the details there, we would have x minus a, but a is -1. So I have that. K going from 0 until infinity. So no problem about this guy. You always have powers of x plus 1. K factorial, that's fine. That will remain in the formula. So the crucial part here is f upper k of -1. So let's evaluate the first few derivatives and hope that we can see the pattern. Now we start at k equals 0. That's my starting index in the summation. So we're doing f upper 0 of x, but that is simply the function itself. So f of x is 1 over x squared. So that means when you plug in the center of expansion, we will get 1. All right. Obviously, we cannot guess the pattern right now, so let's try another k value. When k is 1, we get f upper 1, but f upper 1 is another way of saying f prime. So we need to differentiate this guy. This is x to the power -2, so the derivative would be -2 x to the -3, right? -2 x to the -3, yep. And then we need to plug in -1. So we'll get -2 times -1 to the -3. Right? But you can also write this as -2 times -1 to the power. I'm deciding what power to use. Okay, I can use to the power 3. Because remember, -1 to the power n is equal to -1 to the power -n, right? Because yeah, this will just be 1 over -1 to the power n, which will be the same guy as this one, right? So -1 to the power -3 is the same as -1 to the power 3. So here we're trying to find the series expansion for f of x equals 1 over x squared. So the crucial part in finding the series expansion for any function is to find a pattern for this factor, which is the kth derivative of f evaluated at -1. So here I'm trying to evaluate some of the derivatives in order to get a form for that factor, right? But yeah, it looks weird, but I hope my derivatives are right. Okay. Okay, or perhaps I'll just write it as a -1. Okay. Because -1, oops, to the -3 is equal to -1, right? All right. So let's try another one, k equals 2, because here it doesn't give me any pattern so far. F upper 2 is f double prime of x. So we need to differentiate this guy. When we differentiate, we get -2 times -3 to the power x to the -4. But remember, we need to plug in -1. So this would be -2 times -3 times -1 to the 4th. But that will just be -2 times -3 times 1. Right? And then let's see another derivative if the pattern is not yet clear. Let's try one more. And perhaps after this, we can try to guess what happens for a general k. So this is the third derivative. So the derivative would be computed using this guy. So we'll have -2 times -3 times -4 times x to the power -5. And then if we plug in -1, we'll get -2, -3, -4, and then -1. Okay. So for general k, we can have this formula. Let's try to see if we can see the pattern, right? Now let's see. What do we see here? Well, we see products of negatives, right? So let's count how many negative signs do we see. For k equals 0, there's no negative sign. For k equals 1, we'll have what? For k equals 1, I have -1 times -1. I'll have a positive factor, because I will have two negatives over here. And then for k equals 2, how many negatives will I have? I'll have 1, 2 negative signs there, so it will become positive. So it seems that for even values of k, we'll end up with a positive number, right? So because here I'll have a positive 1 when k equals 1. Oh, it breaks the pattern, because here I'll have -2 times -1. But for k equals 2, I'll have negative and negative. That's again positive. Oh, it looks like I'll always have positive factors everywhere, right? Because this will become a positive number. This guy will become a positive number. This guy will have a will be a positive number. So it looks like it would be a positive number. So I don't need to have negative signs all over the place. Now, how about the constant multipliers? Well, for k equals 0, we just have 1. For k equals 1, we have 1 times 2. Oh, that's 2 factorial. When k is 2, we get 1 times 2 times 3. Oh, we'll have 3 factorial. For k equals 3, we have 1 times 2 times 3 times 4. That's going to be 4 factorial. So what do you think will happen if we have a kth derivative? So I hope you see the pattern. When k equals 1, you'll have 2 factorial. When k equals 2, we'll get 3 factorial. When k equals 3, we get 4 factorial. So if you are on the kth derivative, we're going to get k plus 1 factorial. Do you guys agree? Or do you see the pattern? Hello, guys. Are you with me? Do you follow with the solution? Okay, great. Good to know. So that's how you find the formula for f upper k. Try to look at the pattern. Sometimes not carrying out the multiplications is much better, because that will help you see the pattern more than multiplying everything. Because you could have simplified it as 1. This will become 2. This will become 6. This would become 24, and it might not be clear that that is k plus 1 factorial. That's why I kept them in an expanded form in my solution. So this is just a formula for f upper k. So now we know 1 over x squared, which is our f of x, can be expanded as the sum of, remember, we have f upper k evaluated at -1, but I already knew that that guy will simply be k plus 1 factorial. All over, in the formula, there's a k factorial below. So I'll copy that here. And then I'll have x plus 1 to the power k going from 0 until infinity. Now we can carry on with the simplifications. K plus 1 factorial divided by k factorial. There will just be a k plus 1 left on top. And we'll have this expansion. And there we go. That's our expansion for 1 over x squared. Yeah, sure, Murel. Just send your question. How about the others? Is this fine? And again, the challenging part here is really finding a formula for the for the kth derivative of f.
Can you zoom out on this problem so I can take a picture?
Mm-hmm. Sure. There you go.
Okay, thank you.
Mm-hmm. I don't think you'll be given very complicated functions to find the Taylor series expansion of. I browsed through the exercises in this section, and it seems that they're just trying. They just want you to do the basic. Daryl, I wouldn't dream about that. It's a reason why I'm looking forward to ending my studies, so I don't have to take tests anymore, even if it's a Cal 1 test. Okay, let me see the question. Okay, so this is the question Morel sent, Popper. Are you, is this Popper already submitted? Or is,
She gave the popper today.
uh-huh.
And a lot of people are having issues with it, I think. Because a few of them stayed after class.
Uh-huh.
So
But did she already give you the answer to this?
Not really. She just gave us an example, but I think we all some of us still got confused on it.
Okay. Yeah, perhaps I'll give just a similar.
I do think it's C, but I'm not sure.
Okay, let me modify the problem a bit. I'll just change the constants. So suppose, maybe here, an exemption to the general instruction. So let's suppose we're given f of f of 0 is say 5, f prime of 0 is 7, and say f prime of 0 is equal to say -1, and then we let g of x be equal to f of 10x, and we want to find a Taylor's we want to find the Taylor polynomial of degree 2 for g of x. All right, so we don't know how g behaves, except that g is f of 10x. So probably I'll begin with finding a series expansion, or find the Taylor polynomial for f first. Right. So f of x will be equal to, remember, f of x is equal to Taylor's expansion, so it would be sum of f upper k evaluated at 0 over k factorial x to the power k going from 0 until 2, because you're looking for a polynomial of degree 2 for g, but g is very much related to f, so I'll find the second degree polynomial first for f, right? So this guy would be what? So this guy would be the sum of what? F upper 0 of 0 all over 0 factorial x to the 0 plus f of 0 prime over 1 factorial x to the 1 plus f double prime of 0 over 2 factorial x to the power 2, right? And clearly here you see that you have a polynomial of second degree, all right? Now we plug in the constants. F upper 0, according to my problem, is 5. So I'll use that here. So I'll have 5. 0 factorial is 1 by convention. So that will just be over 1. X to the 0 is just 1. So first term is 5. Plus f prime of 0, according to the problem, is 7 over 1 factorial. So that would be 7 times x plus f double prime evaluated at 0, that's -1, over 2 factorial, which is 2 and quantity x squared. So the function f is equal to 5 plus 7x minus 1/2 x squared, right? So this is the function f. But we're looking for the series expansion or the Taylor polynomial for g of x. But remember, g of x is just f of 10x. And do you remember what this notation means? This means that for all x's that you see, you replace just replace x's by 10x, right? So this is your expansion for f. When you evaluate it at x, this calls for evaluation at 10x. So you just replace all x's you see by 10x. So essentially, I'll have 5 plus 7 times 10x minus 1/2 10x to the power 2. Again, I just replace all x's by 10x. And simplifying this will give me this guy, minus 50x squared. All right, and that's it. Is that clear?
Yes, thank you. Can you zoom out so I can take a quick screenshot of it, please?
Sure. There we go. Okay, so I'm uploading this worksheet so you can download everything via my website. But if you want immediate copy, so yeah, you can take a screenshot of these. Let me see, what would be my next example? Have you derived in your lecture the series expansion for hyperbolic cosines and hyperbolic sines?
No.
Okay, so maybe we can play with that. Oh, thank you, Daryl. Yeah, I upload all our class recordings also in YouTube because I ran out of my memory in my Google Drive. And I think it's education should be for everyone, so it should be in the public domain. So yeah. Okay, let's try this one again. Going back to the original instruction, find a series expansion. Let's try a series expansion for hyperbolic sine. I hope you don't mind if I go over time by about 5 minutes, but you can leave when if you need to. Let me just finish this one. Hyperbolic sine. You could also do hyperbolic cosine in a similar way. Again, the series expansion requires this. Let's do around x equals 0, because evaluating everything at 0 is much easier than any number, especially for hyperbolic functions. So this is f upper k evaluated at 0 all over k factorial, x to the power k, k going from 0 until positive infinity. If you notice, I always start with the formula because I'm very bad at memorization. So the only way I can memorize something is if I write it a lot of time. So until now, if I do a series expansion, I start with writing the formula because I cannot remember it on my own. And another thing is that for me, if a student took an exam and was able to write the formula, then I'll give him or her partial credits because at least he or she knew the formula. So they deserve to have partial credits for that. So, okay.
I have a question. Well, do you think they're gonna put hyperbolic sine and hyperbolic cosine in the test?
Well, if they will ask you to find a series expansion of some functions in the test, then the prime candidate would be hyperbolic sines and hyperbolic cosines, because you will see that the derivation will be very simple. Actually, it's much simpler than 1 over x squared or 1 over x. So I'm banking that if I will write the exam and I want to test if you can do this evaluation, then I'll put hyperbolic sine and hyperbolic cosines. But I'm not sure. But if it's up to me, I'll ask you to expand sin x and cos x. Because you will see that the expansions are not that difficult. Because again, we start with some values of k and find a pattern for this guy. So let's start with k equals 0. When k equals 0, we get f upper k evaluated at x. That's just your usual function. That's hyperbolic sine. And we plug in 0. Since 0 is just equal to 0. You go back to the definition of hyperbolic sinh, you will see that when you plug in 0 there, you get 0. The exponential definition, I mean. So when k equals 1, we get f upper 1 of x. That's just the first derivative. Derivative of hyperbolic sine is hyperbolic cosine. Then we plug in 0. We get cos 0. Cos of 0 is 1. Okay. And then when k is equal to 2, that means we'll have f upper 2 evaluated at x. F double prime of x is hyperbolic sinh of x. Then we plug in 0. We get sinh 0. Oh, that will become equal to 0. And you see that the pattern will just repeat because here I'm in k equals 3, I'm supposed to take the derivative of sinh, but that will be cos. And then the derivative of cos will be sinh, and then the derivative of cos will be sinh, and so on. So basically here, this will just alternate between zeros and ones. So if you want an expansion for f of x, which is hyperbolic sine of x, you'll see that you'll have 0 over 0 factorial x to the 0, because the first factor is 0, plus f upper 1 evaluated at 0 is 1 over 1 factorial x to the 1, plus when k is 2, we get 0 over 2 factorial x squared, and then plus you will have 1 over 3 factorial x cubed, and so on. All right. Now what do we see here? All of the even powers will be gone, because if the exponent is even, they will go with a 0, which will make the product equal to 0. So that means if I'm going to sum things up, I will have just odd powers. And how do you generalize odd expressions? It will just be 2 to the power k plus 1, right? Because 2k is guaranteed to be even, plus 1, it's going to be odd. So here summation goes from 0 until positive infinity. And what's the pattern over here? So for the odd power, say when k is equal to 0, we get this 1, right? Then it will go with the 1 factorial. If you got x cubed, it should go with the 3 factorial. So if the exponent is 2k plus 1, then the denominator should be 2k plus 1 factorial. And you can check by plugging in the first few values of k. For instance, for k equals 1, we get 2 times 1 plus 1, that's going to be 3. So we get x cubed all over 3 factorial, and there you go. And the pattern will hold true for any value of x. So this is our expansion for hyperbolic sine of x. And you see the uncanny resemblance of this guy with hyperbolic sine. Is that with the basic sine function? The basic sine function will just have -1 to the power k in front. But without that -1 to the power k, you'll have the hyperbolic sine function. All right. So that's why we can also say that the hyperbolic sine function is an odd function because its expansion only involves odd powers. All right. Similarly, you can do the same thing for hyperbolic cosine. The expansion of hyperbolic cosine is just what? The odd exponent, the even expansion to, I'm using k here, so. And I hope you see why, because you start with a cos. So this would be your f upper 0. This would be your first derivative. Then this would be your second derivative, third derivative, and so on. So that means all of the odd powers will be the one that will vanish in the expansion of cos. And if you compare this with the expansion of cosine, you see the uncanny resemblance because the expansion for cosine has a negative 1 to the power k in front of it. But if you erase that, instead of a cosine, you'll get the hyperbolic cosine. I don't know the exact history between the hyperbolic functions and the trigonometric functions, but this tells us that they are very similar to each other, and the naming of the hyperbolic cosine seems very apt because they are very similar to the trigonometric functions, not only in terms of their derivatives, but also in terms of their series expansions. All right. So, okay, we'll end it here, but I don't know what should be our agenda on Monday. We can talk about errors involving arising from approximations using Taylor polynomials. But if you encounter some problems when you do your homeworks and quizzes, just let me know on Monday, and then we can talk about them. I'm also thinking if there's a practice test that we can try. I'll just see what's in your lecture. All right. Okay, Morel. Let me see. Can you please post the hyperbolic? Yeah. Probably I'll copy. I'm thinking, will I copy paste this above? I'll just leave them here, and I'm uploading this entire worksheet. So go to my website. It's going to be worksheet 20. So just download everything. This guys will be there. Oh, do you mean if I'll? Well, probably I can copy paste Cinch and Kosh on top so that you'll have a sort of a cheat sheet for this. Okay. All right, guys, I have to go. I have another lab class to go at 12. So I hope you guys will have a good weekend, and let's see each other again on Monday. Bye, guys.